And just like the previous one, we started from an ideal situation where we had our amplifier and then the feedback network. In this case, the amplifier was a transconductance amplifier. It takes in a voltage and it gives out a current. So the current is measured in the feedback network, and a sample of it is produced on the other side at the input side that gets added to the input voltage. The net amplifier with feedback can be modeled like this, with an input resistance with feedback under feedback, an output resistance under feedback, and the gain with feedback. Okay, and if you see, it looks the same as the original amplifier that we put it under feedback, negative feedback. So the formula that we knew works for the gain. The formula that we learned from series shunt, the last case, also works here. It was the output resistance that we needed to find out. On the output side, we were also in series. Therefore, it did make sense, as we found that the output resistance with feedback is the output resistance of the original amplifier times 1 plus A beta. Now, in practice, we would definitely have an RS, which goes in series with the source, an RL, and inside the feedback network, we would have impedances or resistances that we need to get rid of. And here we are using Z parameters as a two-port network to model the feedback network, because on both sides of the input and output, we have series combination, right? So now we had to take these resistances out to the amplifier, and we would get rid of the source, this source here, due to the unilaterality of the feedback network. And we would only have one source and a short circuit in the feedback, like this. This would be the ideal situation. Now, the amplifier, a new amplifier that we have, contains RL, RS, R11, and R22. Okay? So when we follow the same things that we learned here, output resistance, input resistance, and the gain, for this idealized type of a network that we have. Right? The only thing is that we need to use the gain of the newly formed amplifier. Right? And another thing that we need to do is, after we finish working with this, we need to give RS back to the source and RL back to the outside of this amplifier. And we do so by subtracting RS and RL from the input and output resistance that we calculated from the ideal situation. So basically, this is what we have: a new amplifier where R11 and R22 are found from the Z parameters of the feedback network. Also beta, which is VF over IO, is determined. And when we have that, and we have the A for this, the new gain for the amplifier, and then we can actually use all those formulas that we found out where we had ideal situation. We went through a couple of examples, at least one maybe, and in this case we practically determined the feedback network, and we had to calculate the R11 and R22, and then we had to incorporate those into the amplifier. Now this would make a new amplifier. This would be our newly formed amplifier with R11 on the input side and R22 on the output side of the amplifier. And then we had to find the gain of this newly formed amplifier. And what kind of gain? The output current over input voltage. Okay, this is the transconductance gain of this amplifier. And then we split this gain into three gains of the three stages that we had. The first two were the voltage gain, and the last one was basically a transconductance gain. And the first two were determined by the Hawaiian dance, more or less. The second one that we wrote it here in terms of GM also could be considered as a Hawaiian dance case, because in the denominator we would have a little RE. GM is 1 over RE almost. And the tricky part of it was this last part, that we had to consider the T model of the transistor, where the voltage across the resistances on the emitter is the VB3, while the current going through those is IE3. And that's exactly what we needed for this gain, for the last stage gain, because the IO was the same as IE3 and the VC2 is the same as VB3. So what this would give us was basically an Ohm's law, that IE3 goes through the combination of these two resistances, drop a voltage that we call VB3, right? So what we are looking here for was the inverse of that resistance, and here is the inverse of that resistance. So we calculated the gain, the transconductance gain of the newly formed amplifier. Then we had to determine the beta, and beta was determined by the voltage VF over IO. And in order to find that, we had to first divide this current between these two branches, and then the current that goes through this branch goes through RE1 as well, times RE1 will drop VF. So this would give us a relationship between VF and IO, bringing IO down in the other side to the denominator, then we would have this as beta. So gain is found by this equation. However, that will give us IO over VS, but often we are interested in the voltage gain of the circuit. So circuit is different than, you see, this is the output of the circuit, but this is the output of the loop. So as any feedback involves a loop, so this is the loop that we can find for this case. Output of the loop in this case is a current, but output of the circuit is a voltage from some other point. But we can relate these two outputs together. And how that works is that this IO, which is IE, is almost IC, and VO is ICR3, RC3 in magnitude. So if we go back to this equation, we realize that, you know, if we multiply IO by RC3, we get VO. So if you're interested in VO over VS, we take the gain that we found here, AF, multiplied by RC3. That gives us the voltage gain. Okay, the voltage gain. Input resistance is calculated this way, and because there was no RS, we didn't have to give anything back to the source. So that this RIF is also the true input resistance to this feedback network. And then it was output resistance, which was a little tricky again. And by output resistance, we mean what? We mean the resistance that we view into the collector of Q3. And for that, we first have to find the output resistance of the loop. And whatever that turns out to be is what is sitting below the emitter of Q3. Okay, so we open the circuit from the loop on the output side. We look down to see what we see. We look up to see what we see. Because both of them are connected to ground, then we are going to have to add them up. Looking down, we see R22, and that's simple, R22. Looking up is a little tricky, again, because, it's RC2 practically, RC2 parallel with this little RO. We call it little RO, but it is really big in value, in magnitude, right? So the parallel of the two is almost RC2. So RC2 remains in series with the base of the transistor. When we transfer to the emitter side, we get it divided by beta plus 1. And by the way, remember beta, in order to distinguish the beta of transistor with the beta of the feedback network, we sometimes call it HFE, or we call it beta F. Okay, so this is the reflection of the resistance in series with the base, which is brought into the emitter. Now what we have is like this, the little RE3 and RC2 of the beta plus 1 is connected to ground, and from the other side is connected to R22, and these are the 2 points that we're looking in as the output resistance of this loop. Okay, so that's the output resistance. However, as we had determined that when we have a transistor with a resistance in the emitter, which this would be ROF. So we found that resistance, we multiplied it by 1 plus A beta. That's what sits under the emitter of Q3 to ground. Looking from collector, we learned that when we have a transistor, that emitter of it has a resistance, this is the formula. And this formula I showed you last time, that is the same as what we had expressed in the case that we were studying for the current sources. Remember? So we use that formula. This is huge, really big. And what does that mean? It means that, this resistance looking from the collector to ground is very big. Okay, so what about the output resistance of the circuit? Output resistance of the circuit is this one, this big resistance, parallel RC3. And RC3 is way smaller than that. So it turns out to be RC3. So basically, we did go through this. We did find the output resistance, but in practice, we don't really need to do that. For something smaller than that, like the output resistance, little RO, whenever we have it in parallel with normal collector resistances, we say that it is too big and the net resistance is connected to the collector is the RC. Okay, now this is huge. So definitely the output resistance of the circuit is that RC3. Okay, that was series. Any question about series or this example? Aiden.
So should we always take it when it's giving us different orientations as series being the looking for current and shunt looking for voltage then?
Exactly. Yes. So in the loop, series is what is on the output side is what matters on the output side is the current. That's true. When it is shunt, it's voltage. Okay, go ahead and send me another knee, please. Thank you. And I will progress advance the slide to the next case. All right, thank you. Thank you for your knees. Let me copy paste it before I lose it. All right, shunt feedback is another type of feedback. As usual, we look at the ideal situation first. Okay, here it is. Shunt. So it means that on the output side, it must be a voltage because we read the voltage in a shunt position. So this voltmeter, it is like a voltmeter, this feedback network. Must read that, and that's why it goes shunt on the output. On the input side, on the other hand, when we have shunt, it means that we are adding current. Okay, so what we are taking in is a current, what we are putting out is a voltage, and that makes this a trans resistance. Okay, now the same formulas that we found we can apply, for this gain. This gain is a voltage over a current, but the voltage of the output of this circuit over the current of the input to this circuit, which is under feedback, can be found by A, which is the gain without feedback, over 1 plus A beta. As we have shunt connection on the input side and on the output, both of them, input resistance and output resistance, will have to be divided by 1 plus A beta to get the input resistance of the network, the entire network, and output resistance of the entire network. So this was the ideal situation. And as usual, again, after ideal, we go to practical case. In practical case, obviously we do have RS, we do have RL. Not only that, but also inside the feedback network, we do get some additional components. But before we get into that, what kind of the two-port network do you think that we should use in this case? We've used hybrid H parameters, we've used the Z parameters for series. Now we have shunt. What kind would fit this one? There are only two more left. Y parameters, G parameters. Which one do you think would go? Yeah. Anyone? Yes, Aiden.
Is it G parameters? I might be, think I'm...
Well, good guess, but 50%, when you have two choices, 50% is, the guess could be right, 50% could be wrong, and in this case it is not right, sorry. It's the Y parameters, because in Y parameters we have shunt components or parallel components on both sides. And we have Y11 Y22, and two dependent current sources. This one gives us the beta of the feedback network. But this one, we can ignore it because this is the one that brings the effect of the input side to the output for this feedback network. And based on assumption of unilaterality, then this is not there, or this is ignored. But in general, this is what we get. So, we have to take the two resistances in a shunt, in both shunt connections of the input and output to input side and the output side, right? And this is what we get then for the new amplifier. This is the newly formed amplifier where we find R11 and R22 by simply shorting one side, looking into the other side of the feedback network for R11 and R22. And for the beta, it would be the IF divided by VO. So IF goes south to north. Notice that. And because that's I1. I1 is the one that goes into the feedback network from port 1. So if we find those, we can use the formula or the formulae that we showed here and find the gain, the input and output resistance. So what happens next? Again, RS and RL does not belong to the feedback network. We have to give them back, and in this case, both are we have to go through the painful way of extracting RS and RL. This is relatively more difficult compared to simply subtracting RS or RL when we had series combination, right? So when we do this, then we are done. We're done. But basically, the art of dealing with feedback circuits, or amplifiers under feedback, specifically negative feedback, boils down to the ability of analysis or analyzing the new amplifier mostly. Okay, that's perhaps the most difficult part of it. So let's go through an example. In this example, we have a transistor with a beta of 100, beta being the current gain of the transistor. And here we have a feedback from output. This is the output voltage coming in a shunt position, joining here like this to the input. So this is shunting on the input, shunting on the output. Output is the voltage. It brings the current into the input. Now, as usual, when we have a circuit like this, we need to run a DC analysis. The previous example in the series configuration, the DC condition was given. Okay, but for this one, we need to calculate it, and it's not difficult. We can simply short the AC signal, the AC voltage source. Okay, and then what we have is that base to emitter is 0.7. So base would be 0.7 volts with respect to the ground. Okay. What is the current going through this 10K? It would be 0.7 divided by 10K, which is 0.07 milliamp. Now, I base goes into the base. This current, which comes here at this node, must bring I base, and that 0.07 milliamp. And at this point, or this node, we also have a beta IB, the collector current, going down through the collector, right? And KCL here at this node give us a summation of the two currents. These two currents which goes through this 4.7 K and drop a voltage across it, DC voltage. So, looking at VC, first we can find VC by adding this voltage, which is this current times 47K, to 0.7, right? This is a KVL I'm writing, KVL around this loop. I can get VC with respect to ground to be 0.7 plus the voltage drop across 47. Also, I can find VC by looking up towards the VCC. So VC is the 12 volts minus whatever the voltage drop we get across this 4.7K. So 4.7 times this current deducted from 12 is also VC. So we write these two equations in which in two of them we have VC and IB as unknown. Okay? And we can solve that. It gives us IB, it gives us VC as well as IC. So we have all the tools, the DC tools for starting our AC analysis. Okay? For the AC analysis, this is actually the amplifier. This is as is. And RF, with respect to a line which goes through the ground. So it's like a two-port network. As you can see, the dashed line, which contains RF and a line of ground. This makes our feedback network, which if we short one side, look into the other side, R11 is going to be RF. If we do the same thing from the other side and look into the output side, then again we see RF. So both R11 and R22 are RF. Okay. Now, removing the feedback network, the remaining is the amplifier, but the newly formed amplifier must contain R11 and R22, like that, in parallel in both cases, with the input and the output. Okay. So this is what we call newly formed amplifier, which contains R11 and R22, and we have to find the gain of this newly formed amplifier. So here it is. The gain of it is the output voltage versus input current. So if we start by the V pi that we have here, if V pi is the voltage due to the input current actually coming to the parallel combination of these three resistances. So that's why we get V pi equal II times parallel combination of these resistances. But on the other hand, VO is this GM V pi, which goes through the parallel combination of RF and RC. Of course, because it goes from ground up, the voltage that it gives us is negative of what we have for VO to ground, right? So that's why we get that negative. But GM V pi goes there. V pi itself is given up here. We plug this in here, and this is what we get, from which we can find VO versus II or over II, which is the gain that we are looking for. This is the newly formed amplifier gain, and this is what the gain turns out to be. Numerically, if we plug in the values, this is what we get. For input resistance, of the newly formed amplifier, and the output resistance is sufficient to look into the input and output. When we look into the input, all we see is the parallel combination of these three resistances. When we look into the output, of course, when we've killed this current source, which is open, it would be RC and RF in parallel. So these are all the information that we need for the newly formed amplifier. If we find the beta, which again comes from the feedback network, which is basically the RF and ground. Okay, it's going to be IF over VO, which is basically minus 1 over RF. Okay, and this is why, VO over RF, we would expect to have a current going from north to south, but this current IF is going from south to north. So there is a negative for that, but VO over RF is the current. And therefore, IF over VO turns out to be minus 1 over RF. So we found beta, we found the A, we can find the gain, we can find the gain, which is VO over IS, but if we were looking for VO versus VS, all we had to do was to multiply the IS in the denominator by RF, right? So whatever we found for VO over IS, which is this much, we need to divide it by RF, which is 10K. Okay, and that gives us this much for the voltage gain. And this is, again, this has nothing to do, not that it has nothing to do, but this is not directly related to the loop, but it is related to the circuit. And for the circuit, we have a VS, we have a VO, so that the ratio of the two will give us the voltage gain. And we have related the gain, the transresistance gain of the feedback circuit, or amplifier with feedback, to the voltage gain of the circuit. Okay, just like the previous case, that we first found the gain that the loop gives us in that specific case, and then we found an output voltage over the input voltage. All right, so the input resistance under feedback, all we have to do is to take the input resistance divided by 1 plus A beta, because we have shunt. Same with the output. We would get the output resistance divided by 1 plus A beta. On the output side, we don't have an RL, you see? So we don't have to extract anything there. But for the input side, we do. And so we have to use this and take RS out of RIF in order to get the RN. Okay? Any question? Is everything crystal clear? I hope so. All right. So let us go for another knee, and then Aniket has a question. Please go ahead. Aniket.
Yeah, hello sir, how are you?
Fine, thank you. And you?
Sir, not able to revise few lectures because I just came back over here.
Okay.
So
Are you now in Canada? Is that
yes,
what you mean?
I'm in Canada now.
Oh, nice. Okay, welcome.
Thank you, sir. So, sir, this R in, R out, are these like the formulas we have derived from the previous lectures? 1 by RIF minus 1 by RS?
which one are you?
R in,
Which
R
one?
out. The R in, R out which we got.
You mean not this, not these,
Not
but
these.
here?
In the box.
Oh, in the box. In the box is. Oh, you probably missed the one that we talked about. It was the series shunt when we were talking about the output resistance for series shunt. So this is your question, right?
Yes, sir.
This is okay. Okay, let me keep that to the end, and I come back to it. All right?
Sure, sir.
Because this is something that I need to go back to previous lecture notes to show you, what that means and how we get that.
Yeah,
All right?
okay, sir. Thank you.
Thank you. Any other questions? Anyone? No? Let me again copy your needs. All right. So now here we are ready to go to the next example actually. The next example, we have an op amp, and this is a type of an inverting op amp. You see, and the non-inverting input is connected to ground, but obviously we don't have a fully ideal situation for the op amp. We have an open loop gain of 10 to the power of 4. We have an input resistance of 100K and an output resistance of 1K inside the op amp battery. Okay. Now, first we need to identify a loop, and here it is. This is a loop which connects the output to the input, to one of the inputs. Okay. So here it is. A loop. What is it connecting? It's connecting the voltage on the output, so it's shunt, to a node at the input. Okay, so it's bringing the current into the input. So it is shunt on the input, shunt on the output. Now, the feedback network is these 3 resistances. So if we want to find beta, we need to go through this, and we will find that. In fact, that's not that hard, and we can look at the current that is going through this 1K versus the voltage that is across the output to ground, which is V2. So V2, which is VO over opposite to I1 actually, but that V2 will cause an I1 going down, which is opposite to IF. That's why we have a minus sign here. But how do we end up like this? We can actually look at the feedback network. We'll come back to these 2 figures up here. These are for R11 and R22. But for the beta, how do we get to this or to this is from here. You see, this is the V2 or VO, which is applied on the output side. We can convert this voltage and the 100K resistance to current source and 100K in parallel with it. Okay, then we have 2 1Ks in parallel with the 100K, and the current of this current source is divided between the 1K and parallel of 1 and 100K. So if we consider the parallel of these 2 as the second branch, the current going through the first branch is equal to or is proportional to the resistance in the second branch, which is parallel of these 2, divided by the summation of parallel plus the first branch resistance. But that times what? That times V2 over 100K. Now, if we bring V2 down to the other side over I1 or IF in this case, that would give us the beta. So that's why there is no VO here. It's 1 over 100K. That comes from here. Now, for R11 and R22, if we short the output side and look into the input, then we see 101 in parallel in series with 1. 101 in parallel in series with 1. And if we look at the R22 through the feedback network, we see that 1K and 1K are in parallel, then in series with 100K. So 100K and 1K, 1K parallel. That would give us R22. R22 goes on the output side in parallel, R11 on the input side in parallel. Now, this is our amplifier, and this is the op-amp with output resistance, input resistance, and the gain, mu. We need to calculate V1, and V1 is nothing but this input current IS coming into the parallel combination of these branches. So these are the parallel combination times the input current in kilo ohm. I mean, these are in kilo ohm times that current. And then for the output voltage, this V1 is multiplied by mu, which is 10 to the power of 4. Then it's divided between 1K and the combination of these resistances. We have 100 and 0.5K, so 100.5, and the 2K in parallel. So 2K parallel 100.5 divided by 1 plus the parallel times the mu V1, right? And then so this would give us VO. So VO will become in terms of IS, because V1 was in terms of IS, VO over IS, which is the gain, the trans resistance gain, is given by this of 4.4 mega ohm almost. Okay. Now, that was the newly formed amplifier gain, A, right? Now, if we look for the gain with feedback, AF, it's going to be the A over 1 plus A beta. And this is what we get. But if we were interested in VO over VS, if we have VO over IS, now if we were interested in VO over VS, it would be sufficient to multiply that trans resistance gain by RS in the denominator. Okay, and this would be the voltage gain of the circuit. Now, for the input resistance, if we look back, we have parallel combination of all these. For the output resistance, we need to kill this source, and we have parallel combination of 1K, 2K, and 100.5. Okay, so here it is, input resistance, output resistance, but the input resistance with feedback is the input resistance of the newly formed amplifier divided by 1 plus A beta. And this is 1 plus A beta calculated here from here. 1 plus A beta. That gives us RIS, and since the real input resistance is in parallel with RS, giving us RIS, we need to take that RF out. Therefore, our in turns out to be slightly higher than that, than RIF. And this is what I will explain, especially to Aniket in a little bit. The VR out that we found divided by 1 plus A beta is again what the gain, the output resistance with feedback, and again that includes RL, and we need to take the RL out. So if we take the RL out of ROF, then that would be this much the true output resistance of this amplifier under feedback. Okay. Any question other than this resistance extraction that I will explain in a little bit? But anything about this example or shunt? I think I hear someone turning on the microphone. Go ahead. Okay. Yes, Vala, please.
Sir, can you explain the beta part again? I'm a bit not sure.
Sure, the beta, yeah. Here it is. So beta comes from the feedback network, right? And the beta for this case is IF, which goes from down up over VO, which is V2. Okay, so for that, here it is. This is the feedback network, and this is the VO. And we're assuming that this VO is like a voltage source. If we consider a voltage over here, we can assume it is a voltage source. Now, this voltage source and this resistance can be converted or transformed to a current source like this, right? Then all these resistances are sitting in parallel. Now, this current source is divided between this 1K and the parallel combination of these two. So this, let me draw this here. So this two are going to be one resistance, right? And that resistance is in parallel with the 1K here. So when we have two resistances in parallel, the current going through one of them is proportional to the other resistance times the input current, which is V2 over 100, divided by the summation of the resistances in both branches. Okay, and that's exactly what we see here. What we see here happening. So
just a quick question, sir. So in that's the two small circuits that you made. We just ignore the load of 2K.
Which circuits you're talking about? So these two up here?
Yeah, because from the main, like the main circuit that's been given to us, RL.
Yes, RL is not in the loop. This is in the loop, right?
I see,
This circuit, this network is in the loop. Right. So we look at the loop and then, yeah, we realize that these three resistances are the feedback network.
Okay, yeah. Now I understand.
And then based on that, we need to find R11, R22, and the beta. So Vala was asking the question, right? Did you get the beta?
Yeah, yeah.
The beta? Okay.
Thank you, sir.
All right, great. So, any other question about this example or shunt? If not, let me go and find the lecture that we had explaining resistance extraction in parallel combination. Let me see, that must be this one. Yeah, here it is. Okay. Let me get it ready. Oh, I have to share it. Yeah. Okay. Here it is. Aniket, you probably missed this lecture, and in this lecture, where we were talking about series shunt. After we calculated the output resistance, which was in shunt position, following the ideal situation, what we learned from ideal situation was that, you divide the output resistance of the amplifier by 1 plus A beta to get the output resistance of the feedback circuit or network. Now, when we do that, there is a load resistance included in it too. So you see, this is the network under feedback, and when we look from the output in, we see the ROF, or what we see, we call it ROF, the output resistance under feedback. Because the amplifier that the newly formed amplifier, that's what we called it, included RL. Why did we include it in the newly formed amplifier? It was because we wanted to make the feedback networks and the entire circuit like the ideal form. Ideal situation was like this. No RL, right? So if we had absorbed RL into the amplifier, and if there was an RF also into the amplifier, our findings from this study, from this analysis, would be valid, right? All we had to do was to find the gain of the amplifier, which includes the RS and RL, and then apply the knowledge we gained here, AF equal A over 1 plus A beta, RIF, which means the input with feedback, Ri times 1 plus A beta, and ROF, RO over 1 plus A beta. However, when it came to the case that we have included the RL, just so that we make the circuit look like ideal situation that we had previously, then we, at the end, when we find that resistance, we need to give that resistance back, because in reality, the RL does not belong to the amplifier. RL is either, if it's an amplifier, it could be a speaker, or it could be the input resistance of the next stage, which most likely is going to also amplify. Okay, so RL is not a part of this circuit. What we found through the ideal application of the ideal case, which we had to include RL, was this resistance. So what we need to look for is one step towards the left of this resistance. So that means we need to extract this from ROF. And when we have two resistances in parallel, when you have two resistances in parallel and you want to find the total, what do? You say, okay, 1 over R total is 1 over R out and 1 over RL. So one is R out, the other one is RL. Parallel of the two we are calling ROF. To find ROF, if we had R out and RL, we would go 1 over ROF is 1 over R out and 1 over RL. So far, so good. Aniket, are you following me?
Yes, that's good.
Okay. Now, you see, from this, in fact, what we need to find is our out. So from ROS, if we take our L out, it means that, we're getting rid of this 1 over RL. How do we do that? Just to find our out, we need to bring 1 over RL to the other side, like this. Then we have the inverse of our out, which is what we truly know is the output resistance of the feedback circuit only. I mean, the circuit under feedback, the amplifier with feedback. No RL in it, right? And this 1 over R out, if we find the inverse of it, will get us to the R out. And what we had in that other slides that you questioned what is it or where is it coming from, is exactly from here. That's the same equation that we found there. This was for R out. The same thing exists for R in. Replace ROF with RIF and RL by RS. Then this R out becomes R in, which we call it the true input resistance of the amplifier under feedback. Okay. Basically, we defined three input resistances, 3 output resistances. See, this is the input resistance of the amplifier, original amplifier. This is the output resistance of the amplifier, the original amplifier. What we see from the eyes of the source is the input resistance of the amplifier under negative feedback, the whole thing, right? But the truth is that this RS does not belong to the amplifier. Just so that it looks like the ideal situation, we sent this RS into the network and considered it inside the network. Now we need to give it back. In the series shunt configuration, it is much easier, or any time that we have series combination, we simply deduct RS from the resistance that we found as RIF. On the output side, the same thing we do. We look into the entire network, we find ROS, but again, ROS is the output resistance of this entire circuit, which corresponds to the ideal case, right? But in reality, the RL does not belong to the amplifier. We have to spit it out. And when we throw RL out, is what we did here, like that, then we have another resistance, which is the output, the true output resistance of the amplifier under feedback. So the true input resistance of the amplifier and the true output resistance. And these notations is what we often use, but I will try to verbally indicate also that what we are looking for when it comes to the exam, for example, the final, so that you don't get confused. So remember the true input and output resistance versus the input and output resistance under feedback in ideal situation. Okay, that's the difference. So you see, we have 1, 2, 3 input types of resistances that we consider, we discuss, and we need to find, and 1, 2, 3 output resistances. Okay, is that clear, Aniket, and everyone else?
Oh, yes, sir.
All right, great. Okay. Any other question? No other question. Next, we will talk about, I believe, the other configuration, which is shunt series. Okay, but in order to be in sync with the other section, which we just finished the second example, we barely finished the second example of the shunt. So we can say that this is the lecture for today, but you're welcome to ask any question you have after this me. You can type me and leave if you want. You can stay and ask questions. We have another 10-15 minutes left. All right. Thank you. Was that all? And Aniket has question, please. Yes, go ahead.
Yeah, sir. I actually missed 2 of your lectures of feedback completely,
Wow.
which were last week, right? Because was having my
Yeah.
flight on one day, and the one of the other days I was like really sort of not able to attend any lecture because of a big flight.
Right.
I was just
Okay.
resting
Yeah.
for 2 3 days. Yeah. So if you can tell me how I can cover that, or if you can just give me a brief overview in 20 minutes of feedback.
Well, I pretty much covered a big part of it at the beginning. If you were here, were you here at the beginning when
Yes,
I went in the review?
I
Right.
came at 6:15. Yeah.
Yeah. So I suggest you go over the lecture notes, and if you need to read the book, okay, go ahead. It's pretty much the same, but you get a better overview when you look at the lecture notes. And come to my office hours if you want, because it will be boring for everyone to sit here and just going over that.
Yeah, sure. That
Yeah.
works as
Hi, could I actually ask who is asking this question? Because I have found some YouTube videos that goes over the topics that we're going over, and I'd be happy to send them over Discord to such person.
Go ahead and send it to me also, please. Can you email it to me, Julius?
Yeah, I'll look into doing that. I'll
Because I am usually interested in finding out what is it that my students look into the Google. Often,
post it in the chat. Could you just post it? Could you? A few people are really interested actually to see it. If you could just post it in the chat, that would be appreciated.
This would be a lot more than a 2-second look through for me. That's kind of the problem here. Is it would be like it would be a little bit more than me just finding a video. I just would suggest YouTube. I've found some before. I don't really have them all. Like my computer is a big mess of saved files.
So Julius, are you saying that you can find what you were referring to?
Not within 5 minutes, type thing.
Oh, 5 minutes. Okay, yeah,
like,
please go ahead and find and then
I'll
share.
send you later, type thing. Is like I'll email them to you. You can just not like. Yeah.
Okay. Yes, actually, I would prefer first have a look at it, because often that's what I was going to say. Often I find that what they are talking about is either wrong or is in a different way. That, when you look at that, you don't understand the lecture notes, considering or assuming that nothing is wrong about it. Okay. But more than 90% of cases, I find things that they are explaining it in the wrong way. Okay. The concept might be right. I mean, the point that they start to the end of the explanation, the two are right, but at the middle, somewhere in between, they are garbage talking, or sometimes they're not correct. Okay. So if you want to make sure that what you are looking at is actually valid, send me the link and I will look through it.
I'll ensure to have it to you by 8 o'clock tonight.
That's okay. Yeah, sure. Right.
So
all right. Any other questions? So basically, be cautious when you go to Google. You know, it's like a lot of other information. For example, you know, I do check with Google when I find something health-wise wrong, not so that I get a prescription from Google, just so that I know the choices, you know. And when I go to my doctor, I bring it up. I say, you know, I saw in Google saying this, that. Now, which one do you think that is valid for me? And if there's any of them not correct, and he often, you know, says, yeah, this is the extreme of what could happen. This is the other extreme. But, you know, this part of it is not what exactly they say. And so there's always an explanation needed for those who are not masters of the topic, by someone who has more experience. So just like my case, you know, when I go to the doctor, obviously the doctor is more experienced than me about medicine, and he can guide me through it. So there's nothing wrong with looking at Google. However, what is wrong is to rely on it 100%. Okay, so yes, I will have a look at it, and then let the class know if that was something that is worthwhile looking at it or not. When the midterm marks will be released. Good question. There was mistakes found, and because I have to go over it myself, so when I find a mistake, I'm putting my weekend to do that. Okay, for that. And hopefully by early next week, the whole grades will be out. Okay. I apologize for the delay, but it's better to have the right thing than, you know, just giving out quickly the wrong thing. Ada.
So just to go on that note, does that mean that when they went over the solutions in the tutorial, were those wrong as well?
No. You know, the marking that they've done, for example, you know,